So before we begin, I'll just quickly let my group introduce themselves. So we are Maroon, our group is Maroon 5. I am Ryan Heiling. I'll now allow them to briefly introduce themselves.
I'm Aviv from California.
I'm Isabella.
Artem Voripur.
I'm
Kevin
Konstantinos.
I'm Kevin Everett.
And our group leader was Brandon. All right, with that said, I'll also talk about the code now. So in order to make our code, what we decided to do is we purposely separated our functions as from our main body in order to keep things a lot more organized, as well as allow us to just basically have a single spot where we can edit our functions, our tables, etc., etc. Moving on from there, as to our actual data, our data was sourced from the medical records of the University of California, Irvine, and it revolves around heart failure data. And it contains 12 different recorded values per patient. These values include age in years, sex as male or female, chest pain, type as in TA, ATA, NAP, or ASY, resting blood pressure in millimeters of mercury, cholesterol in milliliters per deciliter, fasting blood sugar, as long as it's above 120 milligrams per deciliter, otherwise it's 0, resting ECG, normal ST or LVH, max heart rate in beats per minute, exercise-induced agenia, yes or no, old peak, a value measured from the old peak, and slope of the peak exercise, either up, down, or flat, and if they have heart disease, true or false. This data from the University of California was sourced from 5 different locations, being Cleveland, Hungary, Switzerland, Long Beach, Virginia, and Stalogue. With all that said, I'll now allow my group member to move on to the data tables.
We started off with data tables to find the raw numbers while also offering an easy view of the medians and averages of the entire data set. The first 2 tables display the statistics for those affected and unaffected by heart disease. We found a common increase in almost all categories for the affected population. Cholesterol is higher in those affected, resting blood pressure is higher. The rest follow the same trend. This very possibly also explains why those affected with heart disease have a lower max heart rate. An increase in harmful factors such as the cholesterol or resting blood pressure would definitely weaken the heart over time, possibly leading to the heart failure signs we are looking for and we'll discuss later in further detail. Evidently, an increase in these unhealthy factors across the board are signs to look out for when we are making a machine learning model predicting heart failure. The next 2 dynamic data tables are able to filter specific user-controlled ranges for the age of the population. Similarly to the last tables, we separate them by people with or without heart disease. But since age is such a critical factor when predicting heart failure, we also allow the user to easily analyze whichever age group they want to study. In our own analysis, we observed the clear trend of worsening heart conditions as the age went on. With higher heart disease, the older the population went. For example, the population in the age range of 32 to 42 has a mean of 145 for max heart rate, while the population in the range of 42 to 52 has a mean of 134. Although a bit obvious, it is still important to consider the average age for heart failure and the conditions that follow it for a machine learning algorithm. Another aspect to these tables is their use for analyzing the average conditions for each and every age. Our algorithm can analyze whether a person has, let's say, a higher than average resting blood pressure, then our prediction can be much more accurate and precise. Limitations in these tables are the exclusions of string categories such as chest pain type and sex. Our models only allow for numerical data, so the strings cannot be applied. Now on to our next graph, which is heat maps.
So one core visual representation that we chose for our data set is the heat map. So basically this heat map tells us the relation between each numerical variable to each other numerical variable. So for example, variables like chest pain type aren't included in this representation because they don't use any number value for it. So the color gradient on the right corresponds to some value between 1 to -1, with -1 being an inverse proportional relationship and 1 being a directly proportional relationship. and 0 shows no relationship at all. And all numbers in between those values shows varying degrees of correspondence. To view the exact value for each tile, you can just hover over it and see what value is given, or you can just look at the color and approximate. So our heat map correlates large amounts of data, so I'll just mention the most relevant relationships. The two strongest relationships are between heart disease and both maximum heart rate and old peak. So to be specific, the data suggests that patients with a lower maximum heart rate and a higher old peak are at a higher risk for heart disease. Equally as important is the relationship between age and heart disease. And the heat map suggests that a higher age causes a significant increase in the risk for heart disease. Interestingly, age and maximum heart rate also correlate strongly, such that the higher a patient's age is, the lower their maximum heart rate most likely is. And lastly, there's a noticeable correlation between heart disease and fasting blood sugar, as well as heart disease and cholesterol, such that an increase in either variable would increase a patient's likelihood of having heart disease. And now I'll hand it over to Aviv for the box chart representation of our data.
All right, the box chart is comparing all these variables: age, resting BP, cholesterol, max HR, and old peak, and pretty much anything within the box is, that means that on average these people did not have heart disease, and anything outside of the box, the outliers, are people. These ranges are what are more people that are more likely to have heart disease, and so this way you're able to compare. Let's say you're a female, which would be your sex, and then say you're, let's say your resting, sorry, max HR, go to that, is 140, which would mean you're inside of the box. That means you're unlikely, and many people in this range do not have heart disease from recorded data. And anything outside of that, let's say 200, 220, that means people outside of the box are way more likely to have heart disease. And so this is just all these factors you can compare. Cholesterol, go to that one. Let's say 55-year-old man, and you have, let's say 300 cholesterol. That would keep you inside of the box, which means you are less likely for heart disease. And something that I noticed when making this is that some of the data was at 0 cholesterol, for example, because some of the variables were 0 in the columns, and so we added a function that would remove any variable that had a value of 0. So all the data here is well, I guess you could say it's more accurate this way because there's no zero values. And yeah, that's it.
Hello, I'm Isabella. And so basically, when creating another visual, I would create the scatter plot. For a little background on the scatter plot, it just helps to display values for two variables in a set of data. And basically through these scatter plots, I would create a visualization of the data comparing different variables, or in this case, also known as columns, such as chest pain type, resting ECG, and age and cholesterol, which can easily be changed by just clicking and choosing different X and Y variables. Specifically looking just at the age and cholesterol scatter plots, we can see that most older patients, 50 and up, also tend to have a higher risk of developing some form of heart disease, whereas those below 50, still at risk, have a much lower chance of developing it or having it. This also correlates with the idea that cholesterol levels also tend to increase as we get older, as seen in the scatter plot. And basically higher cholesterol levels equal increased risk in getting heart disease due to LDL, also known as bad cholesterol. But yeah, and I'll be handing it off to Konstantinos, who will talk about our swarm plots.
So yeah, another visualization we chose for our data is our swarm or strip plot. And it's just like another way to one-dimensionally plot the relationship between multiple variables. And so for our strip plot, the x-axis can either be chest pain type, sex, or ST slope. And the y-axis can either be cholesterol levels, maximum heart rate, old peak, or age. And once again, the user can select which x and y axis they want the graph to have. And there's also the third variable of whether or not a patient has heart disease. And it's kind of like color coded. So blue means that the patients do not have heart disease, and orange means that they do. And so underneath the strip plot, we also have, once again, an analysis of like each strip plot. And I think it'd be too time consuming to like read every single analysis. But to summarize, a few of the relationships we noticed were that patients with ASY type chest pain were more likely to have heart disease. Patients with higher cholesterol levels were more likely to have heart disease. patients with a lower maximum heart rate were more likely to have heart disease. Patients with an abnormally high old peak were more likely to have heart disease. Older patients were more likely to have heart disease. And male patients were more likely to have heart disease. And lastly, patients with a flat ST slope or an ST slope that goes down were more likely to have heart disease. So yeah, thank you for listening to our presentation.